Here's a problem where we have a buffer, same buffer we worked a little while ago, that we found the original pH of this buffer was 9.15. But now we're going to add 125 milliliters of zero point 0.1 molar nitric acid. Now, because we're mixing two solutions together, the molarities of each solution will change. We have to use our dilution formula, M1V1 equals M2V2, for every chemical that's involved in the reaction every time you mix together two solutions. So for example, in this case, we have NH3 and NH4 plus in our original buffer. And to that buffer, we're adding nitric acid. When you identify every chemical, we have a strong acid added to a solution that's a weak base with its conjugate acid. The strong acid nitric acid will react with the base. It's going to donate a proton. Because it's strong, as long as one chemical is strong in our reaction, this will be a single arrow, a complete reaction, and we're going to make NH4 plus and nitrate. So, for every chemical that's part of this ice chart, we need to do our dilution shortcut, M1V1 equals M2V2. If we do this for the nitric acid, M1 is the starting molarity, which was 0.1. V1 is the volume of that solution used, which was 125 milliliters. M2, the diluted molarity, is what we're trying to solve for. And V2 is the total volume when two solutions were mixed together. In this case, 1 liter or 1,000 milliliters of the buffer was added to 125 milliliters of the acid, which makes our total volume 1125. So the nitric acid concentration decreased from 0.1 down to 0.0111. And we want to carry out a lot of decimal places when we do this so we don't make a rounding error in our ice chart. We're also going to do this for ammonia and ammonium. So here I completed M1V1 equals M2V2 for the ammonia and the ammonium. They both were 1,000 milliliters initially. Notice the total volume for a solution has to be the same for every chemical in that solution, 1125 in this case. And so we have our diluted molarities. This is just the start of our ice chart, because now we have the molarities. Now we can write our ice chart. So the acid donates a proton to the base, and we're going to make more ammonium and nitrate. Using our M1V1, M2V2 values, we get the starting molarity of the nitric acid, 0.0111. The ammonia was 0.3556, and the ammonium was 0.4444. The only one that's a zero was the nitrate, because we didn't have any nitrate before the chemical reaction started. With this ice chart, we know we're going to go to the right because we have a zero for the nitrate, and we know the reaction is going to be complete. So in this case, the nitric acid is our limiting reactant, and all of it gets used up. So we decrease the amount of ammonia, and we increase the amount of ammonium. So at this point, you have to identify what you have left after this ice chart. Zero of the strong acid, because all the strong acid reacted away. We still have some weak base. we have some ammonium, which is the conjugate acid of that weak base, and we have nitrate, but nitrate is the conjugate of the strong acid, and the conjugates of strong acids do not react with water. So after this reaction, we still have a buffer. And when you recognize you have a buffer, you can use the Henderson-Hasselbalch formula to calculate the pH. We had the pKa already, the negative log of the ammonium cation's Ka value. That was 9.25. And then the ratio of base over acid. The base is 0.3445 and the acid was 0.4555. So the pH works out to be 9.13. Notice the pH before we added anything was 9.15. Very small change because we have a buffer. And notice that the change was decreasing. When we added this strong acid, it's going to make the solution a little bit more acidic because look at our ice chart. We're decreasing the amount of base and we're increasing the amount of acid by this chemical reaction. If we had added a strong base, the pH would have increased by a little bit. In this case, the pH dropped, but it doesn't drop very much because that's what a buffer does.